Hey guys, Nick here, and today we're going to be taking a look at how you solve systems of equations. Now, in particular, this video is going to cover the most common scenarios that you'll find in physics. However, this should also be pretty self-contained if you're learning this for the first time in a math class or if you're just back here for review. These will be the kind of things you do to solve systems that come up in natural ways, such as physics problems or even really those on most math tests. So I'm going to give you a couple examples and a couple of key pointers that will help you navigate any system. And last thing before we get started, guys, if you find the way that I present this information helpful, there are plenty of other good resources out there. For example, Khan Academy and the Organic Chemistry Tutor are very good videos on this topic. But if you like the way I explain things, you think it might sit well with your classmates, the most helpful thing you could do would be to drop this video in your class group chats, help spread the word, help get the channel out there. Really appreciate that. Alright, with that, let's get to systems of equations. So, before we get to systems of equations, which are when there are multiple equations at once, let's take a quick step back into Algebra 1 and remind ourselves what we're trying to do in the first place. So in Algebra 1, we learned about how you find the value of x in scenarios such as this. Now, specifically, and this is going to be a theme throughout the video, that isn't really key in systems of equations, but in physics, when you actually do this stuff, I'll ask you to do it in every problem. We're going to count how many equations and how many unknown variables whose values we are trying to find we have. So here, we just quickly take note, it's one equation, one variable, and whenever these numbers are the same, you are good to go. If you have more unknown variables than equations, you're going to be guaranteed to fail to find all the values of the variables that you're trying to find. You are mathematically guaranteed to fail. So before you ever try to solve a system, we're going to always be checking this. I'm going to repeat this throughout the video, and especially once we get to the systems of equations parts. Okay, so we just checked. We have one equation, and we don't know the value of the number x. We're trying to find what value for the number x makes this equation true. So what we would do is our standard algebra where you move things around on both sides by either subtracting or dividing. So in this case you subtract 3 first, and then you divide both sides by 2 to get x equals 2. And again, what we've done here is we found the value of x that makes this relationship true. Right? So if you plug x equals 2 back into here, you get 3 plus 4, which is indeed 7. So we checked that the value we got is correct. Now, at the same time, you can, or not at the same time, sorry. Let's just say, if you want to, you might consider a more complicated scenario where you have 3x equals 9 and 4y equals 16 as a pair of equations, and you're asked, I want x and I also want y at the same time. Okay? Now, again, we just quickly check here. We have two equations, and we have two unknowns. We don't know what x's value is, and we don't know what y's value is. So we are good to proceed. We're not going to get stuck in an infinite loop. Okay, so 3x equals 9. Divide both sides by 3. That's x equals 3. 4y is 16. That gives us y equals 4. And again, if we plug these numbers back in, we can verify that they satisfy both equations. And we plug in x for 3 for x everywhere we see it, and we plug in 4 for y everywhere we see it. Now, here we got lucky in that x and y were separated in the two equations. The second equation didn't involve x at all. So basically, this second equation alone was the same as this first equation. It was one equation, one variable. All you had to do was some algebra to find what value y was. You didn't have it tangled up in an equation with x at the same time. Okay, so with that, let's consider what happens when you do have that more complicated case. And then after that, we'll go to the general case where everything's tangled. So for case 3, so I'll call this case 1, case 2, case 3. So in case 3, we're going to have some tangling up going on. We'll keep 3x equals 9 as our first equation, but this time we'll have 4y plus 2x equals 16. And this time we didn't get so lucky. We can't instantly find what value y has because it's sort of mixed up with x in this equation. And it seems impossible that we could get y and x at the same time, but fortunately in this case, and it turns out even if y were in this equation and it looks like we're totally out of luck, you will be able to do it. Fortunately in this case, there's no tangling in this equation, so we instantly know that x equals 3. And we can use that information in this equation. We can put in 3 instead of x everywhere and reduce this second equation to 4y plus, now instead of x I'm using 3, so instead of 2x we're going to have 6 equals 16. So, 4y equals 10 after you subtract 6, and therefore y equals 10/4, or whatever the simplified version is. So this pair of points, x is 3 and y equals 10/4. If you plug those back into these equations, you'll get the correct relations. You'll get 9 equals 9 upstairs, and you'll get 16 on the left equals 16 in the downstairs. Okay, now we'll go on to the most general case where x and y are in both equations. So for case 4, we're going to do this example problem, x minus 2y equals negative 2, and 7x minus 3y equals 19. Okay, now again, before any systems of equations problem, particularly in physics, but in general it's very good to do too, we're going to check that we have the right number of unknowns and right number of equations. So we have 2 equations here, obviously. And how many unknown variables do we have? We have x and we have y. By the way, we don't count y twice, it's just how many letters do we not know, not how many places does the letter appear in. So great, we have 2 equations and 2 unknowns. So actually, as it turns out, and I'm going to put a galaxy print star around this because this is one of the most important things I tell my students. When you have this matching of equations and unknowns, you are guaranteed to be able to find both x and y. Unless you've written the same equation twice, or just a multiple of the first equation again, you're guaranteed to be able to find both x and y, and that's a very useful checkpoint before you finish off a physics problem. Okay, so we're good to proceed now. And the question is, how can we find both x and y when they're both tangled up? I can't just get x equals negative 2 upstairs because y is stuck there. But at the same time, I can't really find what y is because x is also down here. So it isn't really clear what I'm going to do. And this is where the general process of systems of equations comes in. Now, so I'm going to use this as a motivating example. I'll give you a few statements about how you can attack problems, and then we're going to go back to this example and solve it. So, in general, systems of equations have 2 approach methods. And then also they have graphing, but often graphing will not be quick or sometimes even allowed on tests. You might not have access to a graphing calculator. So we're going to not cover graphing in this video. So the first approach method is called substitution, and that's the one we're going to do first. And this will always work, but compared to the second method, which I'll show you in a second, it can be slower or more ugly. Math-wise. Okay, and again, this galaxy print thing is so important. You need to check if you have the same number of equations as you do unknowns before you start doing this step, because the math can get a little intimidating. It won't be difficult, but there will be a lot of numbers, and it's reassuring to know that you are guaranteed to be able to find the numbers that you need at the end of your process. Otherwise, you can get stuck in infinite loops, okay? So it's very important to check that galaxy print statement. Okay, the second method is called elimination. And this is really effective when one equation and the other equation contain things such as plus 2y in the top equation and minus 2y in the bottom equation, or plus 3x in the top equation and minus 3x in the bottom equation. Okay? Now, as it turns out, this rather exotic situation, this happens a lot in physics. Most notably, you're going to get these systems of equations when you're doing acceleration problems with Newton's laws. And specifically, you're very often going to have ropes, one of which will pull forward, creating something looking like plus 3x up top. And on a different object, that same rope, wherever it's attached, will pull backwards, leading to something looking like minus 3x in your equations. So anyway, the takeaway is that although this is only applicable sometimes, in physics that sometimes actually happens quite a lot, so it's very useful to know how to do this. It'll keep your problems going clean and reduce the chance of algebra mistakes happening. So we're going to take a look at how you do both of these, and I'll show you and point out when you should identify, oh, I should be using elimination here because it's one of those special cases. Okay, so now I'm going to leave elimination for later, and I'm going to tell you the generals of how you do substitution. So for substitution, the main idea, oops, I'm erasing things, is rearrange one equation, and I'll tell you which one might be faster. It doesn't really matter which one, but one might be faster. You're going to rearrange one equation to read something like x equals, I don't know, 5/2 y plus 10. You want x by itself. Or alternatively, you might choose to get y by itself. Y equals 2x plus 5. The real key is you need one variable to be sitting all alone on a side of one equation. So for example, in our motivating example up here, x minus 2y equals negative 2. And 7x minus 3y equals 19. Okay? Just sort of randomly, I'll explain why I'm doing it later, is I'm going to rearrange the top equation. Again, I could have picked the bottom equation, it's fine. I'm just going to pick the top equation and say I want this to read x equals blah blah blah. And all the stuff on the right will not have x's. So I'm going to choose to rewrite. By moving 2y to the other side as x equals negative 2 plus 2y. Oops, erased. Okay, so I've just rewritten the top equation by moving 2y over to the other side. Equivalently, I added 2y to both sides. And I haven't touched the bottom equation. Okay, so we've done the rearrangement. That's step 1 or step A. Actually, I'll call it step 1. Little 1. Okay, step 2 is, now that you have this written so nicely, x is the same thing as this expression, everywhere you see, in this case x, in the second equation, instead of writing x, because remember the whole issue down here is that we can't find y from it because x is stuck in there too. Everywhere you see x, instead of writing x, write out this expression that x is equal to. And by the way, you want to do this in parentheses because x is equal to this group right here. So for example, in the bottom equation, ordinarily I'd have 7x, but now I'm going to have 7 times negative 2 plus 2y instead of x, because x and negative 2 plus 2y are the same thing from the top equation, minus 3y equals 19. Okay, perfect. So we've made a substitution, that's why it's called substitution, into the second equation from the rearranged first equation. Now we're left with this equation, and if we look here, is x still in the equation, or is it just a one variable equation in y, sort of like this at the beginning, where there was only one variable sitting around, which was very easy, we know. Now, there's no x in here because we've killed it in favor of this expression in terms of y. So this actually is just a one variable equation. I guess it's one equation, but it's one equation and one variable. There's no monkey business with another unknown variable in there. All we need to do is distribute stuff out, and we'll get an equation sort of like 5y equals 19 or something like that. And at that point, it's very easy to find what y is. So let's go do that. So I'll write here as it like sort of a checkpoint. Your second equation should now be one variable only. And again, this is like an algebra 1 equation, in quotes, where all you need to do is add and divide stuff. To get y. Okay, so let's do that. We're going to distribute the 7 through the parentheses. Remember, because when you multiply a number into parentheses with things that are being added, you need to distribute it across. So 7 times 2 gives us negative 14. We also need to multiply the 7 into the 2y, so it's plus 14y minus 3y equals 19. Okay, 14y and negative 3y combine into 11y. Okay, our whole goal is to get like y by itself, so let's add 14 to both sides, moving the 14 over to the other side. So now you have 11y equals 33. And now divide both sides by 11 to get y equals 3. Okay, perfect. We've found what y is. And now we just need to find what x is. So sort of like, let me scroll back up here. We had this example here where we were able to find what one number was, and then we were able to just plug it into the other equation and instantly find what the other was. That's similar to what we're going to do here. We're going to look back at our first equation at any stage of manipulation, so this one that we haven't yet fully used, but really we could even plug into this equation. But we now know that y is 3. So we can just plug y equals 3 in to either one of these equations, and it will then tell us what x is. Let's use the top one, for example. So we've actually rewritten the top one in a really nice form. X is negative 2 plus 2y. But we now know that y equals 3. So 2 times 3 is 6. So x equals 4. So perfect, that's our solution. X equals 4 and y equals 3. And if you want, you can actually check that that does work in the original problem. I'll just give you a name for this. This is called back-substitution, because you're going back to the beginning and substituting stuff in. All right, perfect. That's our first example, and by far the most time-consuming example. Let's rip out another one real quick. All right. Example 2 will be a similar looking set of equations. Y equals 3x minus 1, and the second equation, 4x plus y equals negative 8. Okay, let's quickly do our check. We have two equations and two unknown variables. Again, we don't know x and we don't know y, so that's 2. So we are guaranteed to be able to find what x and y is. It's just going to be a matter of doing some algebra. We won't get stuck in an infinite loop, so we can have confidence in that. Okay, now step 1 in substitution is you want to get an equation to read either x equals blah 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 or y equals blah blah blah. Last time we had to move that around, or we had to move the top equation around to get that to happen, right? We started here, it wasn't in x equals form, so instead we rewrote it and we got this improved form where it was just x equals stuff. Here we were actually gifted that from the problem. It's already in the form y equals something, so it's already in y equals blah 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 form. So that step's done. Step 2 is then everywhere we see y in the other equation, we're just going to stuff this in instead. So for step 2, we're going to stuff y equals 3x minus 1. Y will basically just be replaced with 3x minus 1. So our second equation is now going to be 4x plus 3x minus 1 equals negative 8. Okay, step 3 is then to just solve this algebra 1 type equation. Okay, so in this case we have 4x plus 3x is 7x. Okay, we're going to add 1 to both sides. Negative 8 plus 1 brings us back towards 0, towards negative 7. And then x equals negative 1. Awesome. Now we're at the easy part. We get to back substitute. Again, that just means plug in the value of this variable you just found into one of the equations, and this one looks pretty convenient. I can just plug in x and it'll tell me y equals this. So if I plug in negative 1 everywhere I see x, I get y equals 3 times negative 1, which is negative 3, minus 1. So y equals negative 4. So this is your answer. X equals negative 1, y equals negative 4. Awesome. All right, at this point, I'm going to throw a little bit of a curveball, and I'm going to start renaming variables from x and y to the things that you'll most often see in physics. Okay, the process will be identical. It's just x is going to be replaced with another letter. Y is going to be replaced with another letter. However, it is important to be able to do that, and it's actually more difficult than a lot of people think to keep track of what is a variable, what's not, what does each variable mean. So we're going to hit this example. 4 plus t equals, actually I'm going to use f instead. 4 plus f equals 4a, and 8 plus 2t, oh sorry, f again, equals 2a. Okay, now again, we check real quick that we have the same number of unknowns as equations. So I guess I'll call this actually step star, and it's so important, I'm going to make it step galaxy star. And it's 2 equations, 2 unknowns. And we verify that, so we're good to proceed. Okay, little step 1. Our goal is to rewrite one of the equations, so it's just f equals blah, blah, blah. So let's do the top equation. We're going to move the 4 to the other side. And that means our improved set of equations here is f is 4a minus 4. And the bottom one is unchanged. Oops. Okay, perfect. Now, as usual, we're going to take f, and everywhere we see it in this bottom equation, we're going to replace it with 4a minus 4 in parentheses. That way that'll get rid of the 2 variable situation in the bottom one. So that means we will replace f2. So that means the bottom equation is now 8 plus 2, and instead of f, I'm going to write 4a minus 4, because the top equation tells me they're the same, equals 2a. Step 3 is to solve this equation, again, which is just a 1-variable algebra 1 style equation. So I'm going to need to do a little bit of algebra on this. 2 multiplied in distributes, so I need to multiply it in both places. 2 times 4a is 8a, and 2 times negative 4 is negative 8. Okay. Let's see. 8 and negative 8 cancel out, and I get 8a equals 2a. I can move 2a over to the other side by subtracting 2a from both sides. So 6a equals 0. And coincidentally, I made this problem up on the fly. I get that the variable a equals 0 is the solution value. Nothing wrong with that. A equals 0. Okay, and now step 4 is to back substitute. Okay, so that just means, again, you plug your value of a in and find what f is. So f is 4a minus 4, but a is 0, so the first term goes away. So I just get f equals negative 4. Oops. So great, that's our answer. A equals 0, f equals negative 4. And that's the kind of variables you'll see in an actual physics problem. So well done. Okay, at this point we're going to go on to elimination, which is much easier. Okay, now I mentioned elimination. Again, you want to use this in the special case of having plus 3y minus 3y, or potentially something like plus 7x minus 7x, or plus f minus f in your equations. Any of these scenarios where you have one thing being a plus appearing in one equation and a minus appearing somewhere else, you're going to want to use that. And again, these are quote-unquote special cases, but they appear much more often than you might think because physics problems tend to generate plus on one equation, minus on another. For instance, the rope I was talking about before. Now, the idea in elimination is that you want to add equations together. So the stuff on the left of the equal sign gets added to the stuff on the left of the equal sign to generate a new mass of stuff that'll appear on the left of an equal sign. So as an example to illustrate what this means, we're going to have 3x minus y equals 7, 2x plus y equals 8, and first of all, we do check that we have two equations, two unknowns, which we do. So step star has been checked. And we identify, oh, we have plus y and minus y. So if we add these two equations, these will actually cancel. So this makes it a good candidate for elimination. So again, we're going to sort of split it at the equal sign. We don't want to bring things across by accident. We're going to add up all the stuff on the left. So we have 3x and 2x. That's 5x. Oops, I should write it over here. We have minus y and plus y, which gives us 0. So that's actually gone. There's nothing else on that side of the equation. Now we hit an equal sign, and 7 plus 8 gives us 15. Therefore, 5x plus 15 is an improved equation that we can use to help us find the variables. Now, all you have to do is divide both sides by 5 to get x equals 3. Perfect. And now we can back substitute. So we know x equals 3. In any of these equations, we can replace x with 3. Okay, that's 9 minus y equals 7. I'm going to move y over to the other side. And then I'm going to move 7 over here by subtracting 7 from both sides. And we get y equals 2. Awesome. Now, do you see how quick that was compared to the substitution method? That's why this is so great. It's simple, fast, and it reduces the chance of mistakes. But again, you can't use it all the time, so it's important to know how to do substitution. Just off to the side here, I'm going to write our numerical list of steps. So, as usual, our galaxy print will tell us something very important to do. Check equations versus unknowns. Oops, whoa, where have we gone? Check equations versus unknowns. Again, this really applies for physicists or people taking physics. If you are given these on math tests, you're probably already given the right equations versus unknowns. But in physics, it's really essential to check that you have all your equations before you start. Okay, step 1 is to add the equations. And again, these should be divided at the equal sign with that little curly line that I did, just to keep it organized which goes on which side. Step 2 will be to, usually it's only one step, to divide and find what the variable is that you isolated. So in this case, we ended up with a simple equation for x. To find value of the remaining variable. And then you already get to jump to back substituting to find the other one. And again, that was over here. I was just plugging x equals 3 into the top equation to find what y was. Excellent. All right, let's do another example of elimination. Okay, this time we're going to do 3x plus 2y equals 10, and 2x minus 2y equals 5. Okay, as usual, step star, we check that we have 2 and 2, two equations, two unknowns, and we do. So we're free to proceed. Okay, we identify that, elimination is probably a good idea here. Rather than substitution, it allows us to cut steps out because we see plus 2y and minus 2y both appearing. So we'll be able to cancel them out when we add stuff up. So we'll hit up step 1 then. We will add stuff up on each side of the equation. 3x plus 2x will give us 5x. The y's cancel just like last time. And 10 plus 5 gives us 15. Therefore, our improved equation is 5x equals 15. And therefore, we can just, oops, I shouldn't have boxed that. We divide both sides by 5 and get x equals 3. We actually had that in the last equation, but x equals 3 is the same value here. Now, we're already on to step 3. We're going to back substitute this into either equation. We'll pick the top one and find what y is. So the top equation, when we plug in 3 instead of x, 3 times 3 is 9. So we're going to subtract 9 from both sides. Okay, 2y equals 1 now, and divide by 2. So y equals 1/2. So x equals 3, y equals 1/2 is your correct values for those two variables. All right, and let's do one last example before wrapping this up. Okay, we're going to do an example with the f and a variables again. 30 plus f equals 5a. 8 minus t equals 14a. This is a very common thing you'll see in physics in force problems. Oops, sorry, I shouldn't have used t. Actually, as an example, let me first say, let's say you had a third variable t. Before we even start the problem, we want to check we have the right number of equations versus unknowns. We have 2 equations, and how many unknowns do we have? We don't know a, that's 1. We don't know f, that's 2. And we don't know t either. So that would set off a red flag. If you tried to find what f, t, and a were, all from these equations, you would be mathematically guaranteed to fail. So you would either need more information, such as another equation, or maybe you know that t is the same as 2f. So that's an example of the important galaxy star check failing. All right, but we'll go back to the correct example here. This is a common one that you'll see. We identified, do we want to solve this by substitution or elimination? What do we think? Probably by elimination, probably because you have the plus f and the minus f. So when you add stuff up, you'll get them to cancel. So we're going to do step 1. We'll add up on both sides. 30 plus 8 is 38. F plus minus f cancels out to 0. And on the right, we have 5 plus 14 gives us 19a. So our equation is 38 equals 19a. And we can divide both sides by 19. And I think this is 2. Yes. Okay, so a equals 2 is our result. And now we just want to back substitute this value of a into one of these equations. I'm going to randomly pick the top one. 30 plus f equals 5, but instead of a, we now know that a equals 2. So 30 plus f equals 10. So f equals negative 20. And this is going to be your solution pair for what the value of f and what the value of a are that make those equations true. And again, this is very typical of what you'll see in a physics problem. Once you do the math, once you convert your diagram into equations, you're going to get exactly that pair of equations, and it's just a short couple steps away from being done with the problem. Hey guys, Nick from the future here, and I realized that I actually probably should have talked about 2 more things. The first of which is you can, if you have a graphing calculator available, you can solve these equations by graphing them. So for example, if you had the equations 3x minus 2y equals 4, I'm making these up on the spot. If you had this set of equations and you really didn't feel like going through the trouble of doing the substitution, what you can do is you can plot these on your calculator as lines. So first, that's going to require writing them both in y equals form. So we're still going to need to do the moving around, so we'll move the 3x to the other side of the first one. Divide both sides by -2. Okay, and then do the same thing to the bottom equation. Okay, I tried to do it in my head, which I knew was always a bad idea. Okay, we have 8 minus 4x. Divide both sides by -3. Okay, now that you have them written in standard form, if you wanted, you could graph these on your calculator. They'll vaguely look like this, I think. Oops, probably should have given myself more room. I'm just guesstimating what these graphs will look like. Okay, and at that point, if you find what point this is, that solution, right, the x-coordinate of that point and the y-coordinate of that point will be the x and y values that satisfy both these equations, right? Because each line is a set of points that obeys one of the lines is a set of points that obeys this equation. Another line is the set of points that obeys this. Where they touch is the one specific point that happens to obey both equations at once. The actual way you find this point, your calculator has built-in intersection functions. I think on a TI-84, probably TI-83s as well, second trace, which is like the fourth button up top, it's the calc menu, and there's a function called intersect where you'll be able to actually tell your calculator that you want to find the intersection, and it'll spit out where the two lines touch. But this way isn't as useful, especially because if you have access to a calculator, you often have access to a computer, and also, as you can see, it requires just as much rearrangement as solving it the standard way. But I figured I would go over it in case you see it in a math class. Second thing I do want to add on, and this you will probably see once or twice in physics, is what to do if there are 3 equations. Okay, you'll see this occasionally. Okay, we're going to do an example that is solve these 3 simultaneous equations. Okay, now as usual, before we start, we just want to check, oops, can't write 7. We just want to check that we have the same number of unknowns in equations, and we do. We have 3 unknown variables, x, y, and z, and 3 equations. So we are guaranteed to find a unique solution. We won't be going in circles, so that's very good. Okay, now we're going to start our process. Now we're going to do this one by substitution, because substitution is very reliable. However, I will say, before you start these big ones, it's often useful to check if you can do something by elimination. Okay. right? Elimination is where you saw a plus 3x in the top equation and a minus 3x in the bottom. In this one specifically, there's a specific thing that may happen. The specific possibility that you're looking for is, does the sum of all three equations together give anything helpful? Okay, and specifically, this is really only useful in physics because this happens usually when there's multiple objects tied together. Okay, for example, if you have something like this, three boxes attached by a rope, and then there's a force pulling them, and you're asked what's the acceleration of the system. Something like this will often happen, so it is worth mentioning that it's worth checking if you can instantly answer the problem this way. Sometimes it'll instantly let you find the acceleration. All right, but that is just in general. I'm going to show you the reliable way that you can use all the time. So, as before, our goal is going to be to write, this time we're just going to look at two equations, and we're going to, sorry, I misspoke there. Our goal will be the same, and it's to, after checking that we have the right number of equations and unknowns, we want to write one of the equations as y equals blah blah blah, or x equals blah blah blah, or z equals blah blah blah. Okay, that way, just like before, when we look at the other two equations, everywhere we see that variable that we hate, let's say for the sake of example here, we hate the variable z. So we're going to rewrite the top equation as z equals stuff. So if we move z and 4 to the other sides, okay, and then you have the same two other equations. Now what you can do is in these bottom two equations, everywhere you see z, plug in this expression instead. Oops. Again, all this was doing was wherever I saw z in those bottom two equations here, I just plugged in this improved expression. Okay, now if we look at this, this actually is two equations involving only the unknowns x and y. So we've reduced this three equation problem down to a two equation problem. If we simplify this out, let's see, we have x minus 2y plus 3x plus 3y minus 12 equals negative 6. Here I'm just expanding the parentheses. Okay, and now we want to collect all the x's together and all the y's together in each equation. And we'll also move the constants over, move the constants over to the other side. So the top equation is 4x plus 1y equals 6. The bottom equation is 3x plus 4y equals 11. Okay, and now we're back at our friendly two equations, two variables, and you can solve this in the same way. So you start the process again to solve this pair. So again, step one is always write variable equals blah blah blah, and then plug it into the other equation like we've been doing for the most of the video. So for this equation, or for this pair of equations, you again write y equals 6 minus 4x from the top equation, and you stuff it into the bottom equation to get rid of y. Okay, now we just solve this equation for x. Okay, so it's negative 13x equals negative 13, which tells us that x equals 1. And as before, now we can just back substitute. To get y at first. Okay, if we look, we have y is 6 minus 4x, so we know that x is now 1, so that means y equals 2. Okay, and now we just need to find z. So we can back substitute again, right? Because earlier, one of the very first things they did was z is x plus y minus 4. So therefore z is negative 1. So your solution is x equals 1, y equals 2, z equals negative 1, and it's always worth plugging those numbers back in here to check that it's solution, but in this case I know that it is, so I won't check. Okay guys, and that wraps up the video. Thanks for sticking around, and you will be using this systems of equations stuff a lot. So if you like the video, feel free to share it with your classmates if you think they could learn something from it. And also feel free to leave comments on anything you think I could improve or anything that you thought I explained well and should keep explaining. Alright guys, that about wraps it up, and I'll see you in the next video.